We're gonna move into the basically the measurement and use of relative permeability, and I'm going to start by discussing this capillary number dependence of relative permeability. This is something that I didn't learn about in college when I was studying petroleum engineering, and it's got a bit of a small historical background that I can at least mention that. There's the what we're talking about doing is that if you have what we're going to call rock, they're all rock, but sometimes it's referred to as immiscible rel perm curves. And we're going to designate that as KRI for immiscible. And these are the rel perm curves that you would expect to get if you just do standard laboratory low pressure. In the case of gas oil, it would be like a nitrogen, mineral oil, or something like that type of relative permeability curves. Now you can have imbibition and drainage, and you can then also have steady state, which is what we're interested in, particularly for this region 1. And these would correspond to what I'm going to refer to this capillary number, which is symbol is NC, basically is a capillary number that's approaching 0 or equal to 0. Okay, and then so the reason you get these relative permeability curves, the permeability drops to a given phase in the presence of another phase, is because the one phase is blocking for the other phase, and then maybe they're trying to slip through the same pores at the same time, and you get this additional constriction and restriction and extra pressure drop to get the phase to flow at the same rate through the rock in the presence of another phase, maybe 2 other phases. So these rock rel perm curves, they're giving the maximum contribution of the rock pore structure, pore size distribution, connectivity, etc. And then we have on the other extreme, we have what we call straight line, or sometimes, and we'll call them miscible rel perm curves. KRM, and this would be corresponding to an infinite capillary number. That's basically the Darcy, the Darcy, the pressure drop through the core is so much higher, larger in terms of a force acting on the fluids than are the capillary forces of like liquid trying to stick to the rock. All the interfacial forces are overcome by this. So usually the interfacial forces are driven to 0, and we think about these miscible curves traditionally in, for example, gas EOR, maybe surfactant EOR, and if you basically have a core filled with decane and you displace it with butane or hexane or something, then the two are first contact miscible, and you don't really have any forces retaining the phase being displaced by the other. And what, at least what I remember seeing first in the literature about capillary number was in connection with how the residual oil saturation would change from its rock value, I'm just going to say the max value, that could be anywhere for a given rock from 10 to 35%, at these very, very low, I don't know what capillary numbers are, low are, but very low values to very high values, I'll put 10 to the x, high values. And by introducing surfactants or doing something, the capillary number, again, that we usually have velocity, viscosity, that representing basically the delta P term, and then interfacial tension, which is reflecting the kind of capillary pressure term. So what you would see in the laboratory is that you'd see something like this. So as you got to higher and higher capillary numbers, then you could see a rock's residual oil saturation dropping down towards zero as you got to higher and higher capillary numbers. It could be from a high velocity or very low interfacial tension. But you didn't commonly see the whole relative permeability curve changing. Okay. Now, I'll just make a little cartoon of the shape of the relative permeability curve for straight line. Basically, we've got saturation. Pick your saturation, your Kr, and basically for straight line, you have 0, 0, 1, 1, and you assume that this is going. Let's say this is oil saturation, so this would be KRO, and gas KRG, so that would be something like that, a straight line. And then if we're doing the immiscible, then this cartoon is going to look something like this. Everybody knows kind of how these should look. KR, oil, and here I'm going to take it from 1 or some number here. Basically, this is going to, this might, let's say this is oil saturation. So we got gas, relative. So I've drawn it like this, and then it kind of comes down like that, goes towards 0, like that, and the oil, some residual oil, and going up like that. And the curvature, you know, a Corey type equation will actually drop down more like this. So this might be typical for Kr being a function of saturation to a power n, and you might have the same, or it's usually different, the power for gas and oil, and so this would be the phase, and you would have the phase here, and then this would be the phase saturation normalized to endpoints, something like that. So typically for rock curves, this exponent n is ranging from, at the very best, 1.5, and maybe at the very worst, greater than 4 or greater. So if we draw something, you know, it could be same critical, and then it might be way down like that. That would be maybe n of 4 for the oil phase, and the gas, if we draw that from a Corey type, that might come down like that. And you see the crossing point here, where they equal each other, is now down below 0.1, maybe around 0.05. And here, when the n is greater, you've got the crossing points higher. So no matter what real perm curve you use, in the best case, for steady state gas oil flow that we've ever seen from any, like Berea, Benheimer, high perm stuff. Basically, your K or either phase should be less than 0.12 at the crossing point, which is KRG over KRO equal to 1. Okay? So if your rel perms that you're working with have higher crossing point than that, you're being overly optimistic, or you're maybe trying to, so the rock curve will, this is what you normally would have. And of course, the crossing point here is essentially 0.5. Okay?
But immiscible displacement, why would you need relative permeability curves?
Immiscible?
Immiscible.
Oh, immiscible. Well, you could have, the term miscible is a little bit misleading. Because, there are two phases. You injected a gas phase, and if it's first contact miscible with oil, there's still two phases. But basically, you never see them flowing together.
No.
Okay? But if you had a pour where they were flowing together, then essentially they would follow the straight line type relative permeability. So, okay. So basically it's straight line, curved to straight line relative permeability, but we call it I for immiscible, quote unquote, and M for miscible. So this is just to make it clear. Are any questions about that? So this rock curve, or the immiscible curve, will give the maximum condensate blockage effect. Okay, and the straight line rel perm curve would give the absolutely minimum condensate blockage effect. Physically. So if you want to look at the extremes and see whether it has an effect, you can run with n of 3, exponent of 3 or 4, make it really, as bad as you want, and you can run it with n of 1, or let's say maybe not perfect straight lines, 1.5. You can put that in there, and you can run two cases of your model, your fine gridded single well model, and see whether the minimum to the maximum has any big difference on the performance of the well behavior. So that's kind of a starting point for assessing whether condensate blockage is important or not. But these define the outer boundaries. So assuming zero blockage is not the outer boundary. Okay, it's straight line relative permeability. So in reservoir simulation, as far as I know, I don't know the chemical EOR literature, so it could be other people. But in reservoir simulation that I'm aware of, dealing with an equation of state, this first paper was by Keith Coates in 1980, I believe. It was published. It was probably earlier than that. Presented. He introduced a means by which you could change from KRI to KRM using a property interfacial tension. So forget the velocity, because in the kind of modeling, full field modeling and type of modeling he was talking about, you didn't ever have anywhere high velocities enough to cause capillary numbers that would straighten the rel perm curve and drive the endpoint saturations to zero. So he used gas oil interfacial tension as a variable, because this could be calculated in a model as a function of pressure and the gas, equilibrium gas and oil composition. In every grid cell, you could calculate, where there were two phases, you could calculate the gas oil IFT. And then he proposed a model that said that, okay, the Kr that we're going to use at a particular saturation, I'm just going to use oil saturation, will be Fi times Kri at that oil saturation plus 1 minus Fi times the Kr miscible at the same oil saturation. Okay? And then he gave Fi was a function of IFT. It was a function of IFT and to a power. I don't remember some new power. I don't know what I'm going to call it. M. I don't remember the functional form, but it was something like, let's see, it would be something like IFT over some reference IFT to the power M. M would typically be greater than 1, if I remember right. And this was for any gas oil IFT less than the reference. And if the gas oil IFT was greater than or equal to the reference IFT, so this was another parameter that you would have to input, then this would just be equal to 1. So the function basically looked like this: IFT, IFT reference, Fi 0, 1, and then this would go to, let me put the reference a little bit further away. So it looked like this. And it could have a function that went down like that. It could have a function, depending on the value of n being greater than or equal to 1, or if it's equal to 1, n equal to 1, it would go like that. So it gave you a lot of flexibility. And in addition to that, the endpoint saturations, for example, SORG, and I think also SGC, these would also tend towards 0 as the IFT tended towards 0. With maybe the same function. I don't remember the details. But this was introduced, and you'll find it in many simulators and it's mainly for miscible gas injection projects. Okay, so if you're not at miscibility or near miscibility, this will straighten the relative permeability curves if you get close to miscibility. So that's kind of the history of how relative permeabilities are thought to vary with capillary number, which includes both velocity and IFT, or just the effect of IFT for driving the capillary number to high numbers, so that you get the rel perm start straightening and having close to 0 endpoints. So when it comes to condensate blockage, this has, like I mentioned earlier, the capillary number dependence of Kr was Shell, it was University of Delft, and it was Imperial College. All of these institutions were measuring data, presenting the data, and in some Imperial College they tried to also come up with correlations for the capillary number dependence. And then, so this is lab data, and then Feivong and I worked on doing the correlation of the data that we knew of either from the literature or were measured in this JIP. So the two correlations that are out there are, the one is from no, I'm sorry, this is not right. I'm saying Imperial College, but that's not right. That's in London. It's Harriet Watt. I apologize. I'm probably going to misspell Harriet. Is it 2 T's or 1? 2 T's. And Watt, 2 T's. Okay, sorry about that. Yeah, it was, I think Ali Danish, who was, I should know these things, but anyways, Harriet Watt, Delft and Shell, and the correlations came out of Harriet Watt and the correlations that we've come up with. Okay, and what I'll say about the correlations here is that these correlations are very complicated. I don't know how many constants there are, but there are many. There's no default values for the constants. If I remember right, they use saturation as their variable instead of the KGKO. And I think that even though these made their way into Eclipse 100 and 300, I don't think they're used by really anybody anymore. What we ended up doing in the correlation was very, very simple. It gave very good match of the data, and there are default parameters for coming. There's basically two constants. The one constant's the same pretty much for all systems, and the other constant depends a little bit on permeability and porosity. So it's a much simpler correlation. So what basically what you want to know is, how does KRG improve for a given flowing mixture? And when I say a given flowing mixture, I'm talking about a certain RP within region 1. Okay? As you go from low values of capillary number towards high numbers, high values of capillary number. Okay?
These correlations, they are still in the same paper, 1995.
No, we're going to get to this paper. I think I put it up here at the top. This 56,476. I think that's where we maybe published the actual correlation. So we'll come back to that. Okay. So I'm going to put in KRG immiscible and KRG miscible. So the behavior should be something that's basically following this line until you start getting some capillary number effect, and then this will increase, and then you're going to have to, basically it's going to be limited by the straight line behavior here, as this is limited by the rock curve. So this is going to be turning and then flattening towards this value here, straight line. So that's what you want to have. Now the question that, how do you make these measurements and then do correlation? So what we argued is that you're basically, if you say, I want to know at a given point in the reservoir, in the region 1, if I'm at a given pressure, which is somewhere between PWF and P star, okay, and I'm flowing through this mixture composition, Z well stream composition, through the core at a fixed pressure, okay, at some fixed pressure. So what do we know that at that fixed pressure is that no matter where you are on this rock, no matter what the rel perm looks like, at this particular pressure, for this particular mixture, it has a fixed ratio KRG over KRO. We know that, okay? Because we've already, this is a steady state flow test. You just flow at steady state at that pressure, and you do it at 5 different velocities, okay? Covering down here, 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 and here, okay? And the only thing that you're changing is the velocity. You keep the pressure, and you can measure this. So for every one of these points, it has the same KG-KO ratio. It's a simple test. The other thing is that the change in KRG has to be the same as the KRO in order to maintain the steady state. So this guarantees that the impact of capillary number is equal for each point on both phases. Otherwise, the KRG KRO would not be equal. That would not remain unchanged. So basically we said that you should make a simple measurement, and all you do is you just change the velocity, the pump velocity of injection. Okay, you inject the same mixture just at different velocities until it reaches steady state. Each time you get the pressure drop, and you know the rates of each phase, and you get the permeability. So this line, the way we did all the correlation work and the way our correlation works, this is for a fixed KRG-KRO ratio. Let's say equal to, well, let's just take the crossing point, okay? It could be 0.1, it could be 10, it could be 100, it could be anything. All you do is measure the pressure drop at different injection rates. And because the KRG-KRO ratio remains constant, the improvement in KRG that you're seeing here, going from here to here to here to here, must be identical with the improvement in KRO. Okay.
I have a question here. Because for immiscible, you say that the KR-KRGO ratio, let's say crossing point when they're equal, should be less than KR should be less than 0.12, you said, right?
Yeah, so this
But
number,
we-
so let's say this is 0.1.
yeah. Okay, so when we move to straight lines, this KRG or KRO is then it's becoming higher.
It's going up
Or is
towards
it
0.5. Because for a KGK, they cross, where they cross for straight line, it's equal to 0.5.
Okay, but this ratio of KRG over KRO always should remain the same. That's where
The way we're doing the experiment here, yes. Okay.
Even if you move to high capillary numbers, this ratio is not changing. It's always remaining the same. Right?
That's right. Because when we went through the
Okay.
steady state flow of the theory this morning, we did the calculations. It doesn't matter what the rock relative permeability is like. It can be like cement or not steel, but it can be anything. If you're flowing steady state through that porous media, then the KGKO ratio is given.
It's only a function of pressure and composition.
Only a function of pressure and composition.
And here, when you are flowing at different rates and you're measuring the pressure drop, then the average pressure should be the same.
Right.
Yeah.
So you basically create this into, you need to keep the pressure the same or close. Yeah. It can be the same outflow pressure, et cetera, et cetera. So
no matter what is the shape of the rail terms, when you move to the straight lines, this KRG, KRO should be kept as it was initially. It should not change.
the ratio will never change.
The ratio, yes.
As long as you float it long enough to reach steady state, it's given, God given. You can't. Rock has nothing to do with it. It's pure PVT.
Okay.
Okay. So if you look at this point here, the rel perm curve looks like this, essentially, right? And the oil saturation is 0.5. The KR is 0.5. Okay. And then if we go down to this one, I'm going to sketch that. It's a pretty damn small sketch, but I'm going to make it look like this. Something like that. So now this is 0.1 and this is 0.7 or 0.6 or something else, right? So the saturation is different here, 0.7, 0.5, but the KGKO ratio is the same. And so we basically did our own measurements. We took the measurements of other people, and we found how this equation transitioning from immiscible to miscible, basically we found a functional equation for this, a functional form for that transition. And as a function of capillary number, and I don't remember it, so I'm going to have to go find. This paper here. It's somewhere. Okay.
I have another question, might be out of the scope of this course, but have you ever tested that for water and oil rail forms? Just out of curiosity, maybe.
Water, oil, like water with surfactants?
Yeah, would this ratio still remain the same?
Oh, yeah. You could set up the steady state condition for water, oil. I've never done it. I'm not sure how trivial it would be. There's no phase behavior, so yeah, there's definitely I've never done it, so I'm not going to try here and now, but yeah, I mean, there has to be the same concept, because basically if you inject oil and water at some proportion, 0.7 water cut or whatever, however you want to define it, through a core, and you just continuously inject that same, eventually it's going to reach steady state, and what you flow in is going to be exactly what you flow out, right? But the saturation in the pores is not going to reflect that ratio of 0.7. So there will be an equivalence to the steady state and to the relative permeabilities that give that steady state condition. And depending on the rock curves, you can have a very different oil water saturation distribution for one rock versus another, but the ratio of KRW to KRO will be the same, I think. Have to be. Okay. So this here is the equation, miscibility for Fi using that same equation as Coates gave. 1 over alpha capillary number to the power of alpha, no, power of n, sorry.
Okay.
And then plus 1. And I think n, we pretty much always use something close to 0.7, if I remember. Let's see here.
Okay.
Does it say 0.65? And then alpha was found to be a function of permeability and porosity. And this average permeability between the immiscible and miscible. So this is the correlation. Let me just get a snip. Right. Anyway, so this is the equation. Okay. So, once you set, once you have KRG, KRO, you know that, okay? That will immediately give you KRG immiscible and KRG miscible, okay? You get those immediately. So then that then gives you this KRG average, and then that gives you alpha, which is equal to alpha naught over KRG average, and alpha naught you can estimate from this 10 to the 4th over square root of KP. That'll vary for each rock. So now what we found, most of the data when we developed this correlation was for, I would say, higher permeability rocks. People were measuring on Berea, Benheimer, and in the North Sea, the companies involved in we're like looking at 10 millidarcies up to a darcy. And then as time has gone over the last 20, 25 years, we've looked at lower and lower perm rocks. And I'm going to ask Singh, this, we haven't republished a correlation, but this alpha 0 for lower perm rocks should be modified. That 10 to the 4 should be changed to something else. I don't remember the number. We'll get that from Singh here in a little bit, unless he jumps in. Okay. So this is basically a correlation. I think I've got the presentation of this. Has got some of these figures that where did it go? Oh, not paper, but presentation. Yeah, so I thought this would be an appropriate to introduce this, where basically this paper introduces the capillary number dependence correlation, and it runs and shows how that affects the performance of gas condensate well rates. Now, what I want to do first is just jump to the data, some of the data examples that correlate with this relationship. Yeah, so this is an example of some of the data that we measured both on reservoir and synthetic gas mixtures on the same rock. And you can see this is an example for a KGKO. I'm not sure. I think it's not 1, but maybe 2. All of these points have the same KRG-KRO ratio. I think it's a value of 2. And that's so for the different mixtures we would get this, and we basically fit the equation. This is actually for that Bala field I was talking about. This was data that was measured. I think Marathon did the measurements at reservoir conditions, and then here you're seeing the capillary number effect for these. These were mainly low IFT and somewhat higher velocities. I think that Marathon did that work. They got the high capillary numbers by creating mixtures at high pressure and very low IFT. And this is just an example for all of the data. I think for this and other KGKO ratios, so for the entire data set, basically gives a plus minus 15% on the KRG for all mixtures and all capillary numbers that were measured. So are there any questions about conceptually what's being done?
Yes, I have 3 questions here.
Okay.
If you can move to the equations.
Okay.
Is average KRG, is it evaluated for every ratio of KRG over KRO?
Yeah.
So alpha is constantly changing depending on.
Exactly.
Okay, because in one of your example Excel files where you compare the Eclipse standard model with your capillary number model, alpha is fixed value of, I guess, 4,000 or something.
Are you sure it's not alpha 0?
That's why I asked. No, it's directly alpha. Alpha and N you define as fixed values, and then, yeah.
Okay, that either could be an error in the Excel sheet, but it's it should be. I think the equation here is definitely correct. So,
is it one of the Excel sheets?
Okay, but it's not the endpoints. This average KRG, it's really at the rel-perm ratio.
Yeah. So this correlation that we're using here does not alter the endpoints. because it's only applied to steady state flow regime. One of the participants is saying that in one of our Excel sheets, might have been Bob Mott's when he started the course, that there's a calculation of capillary number dependence, and that the alpha is a constant and not being, because here the KRG average is a function of the ratio.
Yeah.
And so that alpha should be corrected for, alpha will change for each KGKO ratio.
No, I think this was published after this. We found that this KRG average should not be there.
Okay, is that in the final paper?
Yeah, so we don't have any published data, but after doing all those live experiment measurements in the last 20 years, we found that if we have simply alpha without dividing by KRG average,
okay,
then that gives a better result.
Okay.
But that we have not documented anywhere.
We haven't published that.
No, that's good.
Okay. So what you're saying is that basically using alpha equal to alpha naught is better than including this, than using with the KRG average.
Yes.
Okay. All right. That I wasn't aware of. In addition, I mentioned that for the lower permeability rocks, this, now in Eclipse 100, is it implemented as it's written here?
Yeah, so that's the reason we do both calculations. So whatever we are doing the calculations now, and whatever we give to the client, we give in the same way.
Using
the paper.
Okay, so Eclipse 100 is using.
Yeah, using the paper.
But you can get a better fit without it.
Yeah.
Okay, well then that's. But you can't implement that into Eclipse.
That's good.
Okay.
So that's why we didn't talk about that. But if you give some other relation and you don't give the equivalent to Eclipse 100 or 300, then it will create problem. Okay,
you can. All right. And what was this constant changing to for the lower perm rocks? Like we're talking 0.01 millidarcy to 0.1 millidarcy range.
So it goes from 1,000 to 5,000.
From 10,000.
Yeah. So it varies between 1,000 and 4,000-5,000.
It's very
instead of 10,000.
Okay.
Yeah.
Between
1,000.
1,000
and 5,000
to 5,000.
So if you don't know, then we generally use 2,000.
So a factor of 2 less to 10 less. Okay, so definitely less, lower. Okay. All right. So really that 10 to the 4, there should be some permeability dependency there. Yeah. Or the permeability dependency below is not the right exponent, something like that. Okay.
I think this whole discussion was too advanced. Like, can you explain it to people?
Okay. Yeah, so to use this capillary number dependence correlation, you have to pick either this method here, where I think in Eclipse 100 you can specify the
Alpha 0.
The alpha 0, you can specify it, or it can be calculated by correlation.
No, we have to specify.
You have to specify. 0. Okay, so this has to be specified.
And then n, a small n.
Specify in at least.
I think not alpha 0, but the 10 to the power of 4 you can change.
Okay. See? He's saying that you can control the value of 10 to the 4th in Eclipse.
I think because it's a function of permeability and porosity that varies for each grid set, right? So that should be calculated in Eclipse with the grid set properties.
Yeah, yeah, maybe that one. There.
Okay, so I'll have to check that. This number here, specified, and the number here.
Yes.
Okay.
And the alpha C0, yes.
The
Alpha C0.
alpha.
No, it's fine. Thank you for saying that we can, because they use different nomenclature. Then they use alpha C0. So that's 10 to the 4 can be changed. So that's really fine.
Okay,
Yeah.
the keyword is alpha
C0. Yeah.
C0.
We can keep it at 10 to the 4.
Okay. You know, basically when you get this kind of data that I showed you in the paper here, you have two constants to fit. You have the exponent n, and you have this alpha to fit that data. That's basically what. So it's not.
Okay, so this KRG average can be left out. It's still good, adequate model, because without KRG alpha, KRG average, it's much easier for the excellence. Alpha is then constant.
Yeah, but we have to use the alpha average, because if you want to use the result in Eclipse,
Yeah.
Eclipse.
Then
Yeah.
So then we have to use this relation.
Yeah, so the ECL is using this.
Yeah.
So.
Okay.
Yeah.
And the KRO here is then just evaluated as KRG divided by the ratio, yeah?
The KR.
Oh.
KR. Yeah.
Modified
Yeah, KRO is just is just KRG at Capillary number over the KRG KRO. Yeah, exactly. Which you start with here. You always have the KRG KRO. That's the starting point.
There is also another possibility in Eclipse to use also this transition function to estimate the KRO. So there are two options.
In capillary number model?
Yeah, you have two options to do that. One is via the ratio, or one you apply the same transition function f to estimate also the KRO.
It's the same transition function as by Harriet Watt, by this Henderson model.
Yeah,
No. I mean,
without endpoint change.
Without endpoint change, but using this f function, which is. I mean, if you open the Eclipse manual, there are two options.
Okay.
But they also state that the preferred one is to evaluate it with the ratio. So to only have it based on two parameters.
Yeah, I wasn't aware about having the ability to calculate the KRO from any other means than this. I think we just have to look at it.
Yeah, then I have to, if there is some changes, then I have to.
I don't see how it could be consistent, because getting the KR, well, I mean, if you just apply it with the KRO, you would go and you could get the KROI and the KROM. You could do that knowing the ratio. And those would give, those would give a different alpha O, which would give a different, a different alpha, because the KRO average would be different. So that would give you a different F of I for each phase.
No, it's not the same transition function for the KRO. a standard transition function by the Harriet-Watt model, where you also have the normalized capillary number, and then two parameters which you have to determine by experiments. But just to leave out the endpoint change from this model, which would be the third parameter.
But you're saying that my understanding was one of you had said that this model here, you could have a different FI for the KRG and the KRO. Is that?
That is possible, yeah. You can choose whether KRO is evaluated with the ratio, as you also explained, which is also stated as preferred method. Or you can also evaluate KRO with this other transition function by the Harriet-Watt model. But then you have two parameters which you have to determine by lab experiments.
Are you saying you can mix the two models?
Yes.
Okay. I would definitely not do that. I mean, that's a bit bizarre. I mean, first, you would start with the KGKO. You would correct the KRG with our method. You would find a KRO with another method. The ratio would no longer be the correct ratio.
Yes, for sure.
So I would definitely stay away from that option if they let you do it. Because in the grid cell, you can be 100% for sure what is the KGKO ratio, what it should be. And so if you put in different ratios, then it's a non you yeah that doesn't make sense. I didn't know that you could mix the two methods.
Okay. Maybe some client asked them
Ask
to
for it.
implement
Yeah. Okay.
Maybe as a last question, and we will probably also come to this if you go to the slides of the paper. You state in the paper that there is some evidence that the steady state KRG over KRG-KRO behavior is independent of the fluid system, and you refer to some measurements made by Hammond Idles. There's also some figure here. Maybe you can explain on that.
This one here.
No, it's a figure shows KRG measured over KRG-KRO ratio. Figure 6 in the paper, but presentation.
Okay.
This one, yeah.
Yeah, I suspect this is, I think this is the same data, but this is with all the different KGKO. Yeah. I think the one data in that other figure I showed was for something here. Okay. This is for low, but these are all low capillary numbers, so there's no capillary number dependence here.
It's only for the immiscible case. But is the conclusion correct that it's not really or the KRG over KRG-KRO is independent of which sandstone we have and what SWI we have, and also whether we have reservoir gas condensate or synthetic gas A or B?
Yeah, I mean, that's what the data is suggesting. It's not like a great, perfect relationship, but that's what it's suggesting. That there would be dependence on the fluid system. It's a little bit like saying, well, does Darcy's law apply to oil A and oil B both? I mean, there's nothing. I don't think there's any logical reason I can think of that if you have a real reservoir condensate A or reservoir condensate B or reservoir condensate C, why the rock curve of rel perm at low capillary numbers would be different. I don't know. that would be like saying that rel perms you get in the lab with nitrogen mineral oil are not applicable to when you go to the actual gas condensate system, or to, yeah, I mean, that the rel perm data you're getting for anything is dependent on the fluid system.
Is it dependent or is it independent?
Yeah, it's normally considered independent.
Independent.
And this figure is showing it's dependent.
No, but
Not,
for
no,
different
not
rocks,
really.
But
It's,
this is for different rocks.
these are different cores, but for a given core with, I think, actual reservoir fluid, I think we have Berea 2, we have both synthetic gas and Berea, same core with gas condensate, reservoir gas condensate. This
So
closed circle and open triangle. So there's not a lot of difference in these. Closed circle, open triangle. Closed circle, open triangle. I mean, it's, yeah. I mean, I think the general assumption of the immiscible curve being independent of the fluid system is a good one. With and without water saturation, maybe not so good an assumption, but
Because if we stick with this conclusion, then the whole process of getting a reasonable rel perm for gas condensate systems would be much simpler. You just, out of your PVT model, you get the range of relevant KRG, KRO. Then you look into this plot and get the KRG corresponding to this. And then you use the two default values for higher capillary numbers. And you're done without any measurements in the lab.
yeah. So the problem is that these curves, I mean, if you look at the pore size distribution effect, then the immiscible curve coming from the core equation is not the same for every rock. We know that. We know there's a range. I don't know. It's not in this paper maybe, but it's in this other paper we showed earlier, where you've got the immiscible curve, where I showed KRG versus KGKO for different pore size distribution. That's the range of expected immiscible curves. Okay, that's really what that covers. Am I? Let me just go back to this this paper here. Presentation of. Where was it headed this morning?
I just
Okay, this figure here, 17. This is the expected range for all rocks of the immiscible curve, in a sense, okay? Just based on a Corey type model.
Yes, okay. So maybe if you define your pore size distribution, you can correct your KRG plot to this.
Yeah, I mean,
But for a rough estimation, you can maybe live without any measurements, isn't it?
yeah, so we're going to talk about that in this last session, because what we're going to talk about is, first you want to look at modeling, where you use a range from very optimistic to very pessimistic rel perm. Okay, and then you can identify if you see a big effect on the production profile, production performance. Then you need to make the measurements to find out, is it this pore size distribution? In other words, the crossing point here for this quarry is around 0.1 at the lowest, but we've seen cores after cores for tighter rock that are down in the 0.03, 0.04 range. Okay. And so if the rel perm and the blockage effect is important, then you kind of are obliged to measure rel perm. So you know whether it's crossing point at 0.03, 0.1, or 0.12. And the capillary number dependence is the same thing. You know, what's the... But in this early phase where you don't know anything, you do have reasonable starting point for KRGI relationship. Just pick one of these, okay? And maybe one pessimistic one with a crossing point of 0.05, for example. You have to use kind of different exponents for the gas and oil maybe to get that. But you create kind of a pessimistic KRGI curve, and then you just run with the default correlation for capillary number dependence, and you can run your model. And if you see that there's a big difference in performance between the crossing point of 0.03 and 0.08 and 0.12, if it's a big difference, you need to go make some measurements to figure out which one it is. That's the presentation we're going to make here soon. And before you know anything, even if condensate blockage is an issue, you have a very good starting point to do basic calculations, pessimistic, optimistic, just to bracket, is it a problem, is it an issue or not?
That is very helpful.
Yeah.
Thank you.
Yeah. So, okay.